Hello viewers, in today's session we are going to discuss one important problem from homogeneous differential equations of this type where we have dy over dx is equal to f of y over x, right? So in this type of homogeneous differential equation we have in one side the derivative of y with respect to x, that is dy over dx, and the second or the other side it contains the function of y over x, right? So here we have to solve this differential equation, which is x dy over dx plus x cos square y over x is equal to y, and the initial conditions are y of 1 is equal to 0, right? So what we will do, we'll first express this equation in this form, that is in the right hand side we have dy over dx, and in the left hand side we have dy over dx, and in the right hand side we have f of y over x, right? So some function of y over x. So let us here transpose the terms. So let us write this equation as x dy over dx is equal to y minus x cos square y over x. So taking this term to the right hand side. So now let us divide both sides by x, so that here we have only dy over dx. So now we have dy over dx, and here we have y over x, dividing both sides by x, and here x get cancelled, so we have cos square y over x, right? So now we can see that this is a function of y over x. So we can treat this function as f of y over x, and the detail about the homogeneous functions is already discussed in our previous videos. So here we have this function that is of y over x, right? Now to solve these kind of differential equations, what we do, we make the substitution that is y over x is equal to v, right? Where this v is a function of x. So now we can make this substitution as y is equal to the product of v and x. Now if we differentiate both sides, then we get dy over dx, and here since this quantity v is a function of x, so we have to apply the product rule for differentiation. So we'll get v plus x dv over dx, right? So now we'll make this substitution in this equation. So dy over dx can now be replaced by v plus x dv over dx. So here we have v plus x dv over dx, and here we have y over x is v, and then we have cos square y over x is v. So here we have v. Now this v and this v get cancelled, and we have x dv over dx is equal to minus cos square v, right? So by making this substitution, we have reduced this equation into this form, and we can now easily see that this is a variable separable form, right? So we can take v to one side and x to the other side. So now we have dv over cos square v, and here we have minus dx over x. Now 1 over cos square v is secant square v, and here we have dv, and this is minus dx over x, right? Okay, so now we have the separable variable separable form. We have v on the left hand side and x in the right hand side. So now we can integrate both sides, and here we can take the constant of integration as c, right? So now the integral secant square v is tan of v, right? Because we know that the integral secant square theta d theta is equal to tangent of theta. So here we have tan v, and here we have the log of x, because the integral 1 over x dx is a log of x, and here we have c. Right now, to merge these quantities, that is log of x and c, we can here appropriately take c as some other constant, say log of k, right? So that we can combine c and logarithm of x. So here we have minus log of x plus log of k. Right now, log of k minus log of x, we can write log of k over x by the properties of logarithms, because we know that log of m minus log of n is equal to log of m over n. Right, so now we have tan of v is equal to the natural log of k over x. Now taking the tan inverse of both sides, we can now write v is equal to tan inverse logarithm of k over x, right? So v can now be replaced by y over x. So here we can write y over x. Now taking this x to this, we can multiply tan inverse log of k over x by x. So we have y is equal to x times the tan inverse of logarithm of k over x, right? So this is the general solution of this differential equation, right? So now let us make use of this initial condition to get the value of this constant of integration k, and then we can get the particular solution of this differential equation. So now the conditions are y of 1 is equal to 0. It implies that when x is 1, y is equal to 0. So we can substitute these values in this general solution. So we have 0 here, then x is 1 times tan inverse, and we have the natural log of k over 1. Now this is 0 is equal to tan inverse logarithm of k, right? So now we can solve this equation for k. So we can take the tangent of 0, and here we have log of k. So tan 0 is 0, we have log of k, and then k can be written as e raised to 0, that is equal to 1. Right, so the value of constant of integration k is equal to 1. So we can now get the particular solution by substituting k is equal to 1 over here. So the particular solution is y is equal to x tan inverse the natural log of 1 over x, right? So this is the particular solution of this differential equation, provided the condition is y of 1 is equal to 0, right? So this is how by making use of this substitution, we can solve these kind of differential equations. So now let us take one more important problem. So here we have to solve this differential equation, x times e raised to minus 2y over x plus x dy over dx is equal to y, right? So here again what we will do, we'll first express this differential equation in this form. That is, we'll separate dy over dx and the remaining function. So here we can now write x dy over dx, then we have y minus x e raised to minus 2y over x. Now dividing both sides by x, we have dy over dx is equal to y over x minus, here x get cancelled, we have e raised to minus 2y over x. Right, now we can see that this is a function of the form that is f of y over x, right? Now we'll make this substitution, that is y over x is equal to v. Again, v is a function of x, and then y is equal to vx, and differentiating both sides with respect to x, we have dy over dx is equal to v plus x dv over dx. So here we have used the product rule, that is dy dx of uv, where u and v are functions of x. So we have u dv over dx plus v, and then we have du over dx, right? So now this dy over dx can be replaced by v plus x dv over dx, and here we have y over x, that is v, then we have minus e raised to minus 2v, because y over x is v. Now this v and this v get cancelled, so we are left with x dv over dx is equal to minus e raised to minus 2v, right? So now we have got a differential equation with the variable separable form. So here we can separate the variable v and x, right? So we can now write dv over minus e raised to minus 2v, and here we have dx over x, right? Now integrating both sides, and here we have c as the constant of integration. So now we can take minus here outside the integral, and we have e raised to 2v, taking e raised to minus 2v to the numerator, and we have dv. Here we have log of x, right? And here we have c as the constant of integration. Now the integral e raised to 2v is e raised to 2v over 2, and here we have log of x, and here we can replace this c by some other constant, that is log of k, right? So that we can combine these two terms, right? So for the simplicity or the convenience, we can take c as the log of k, where k is some other constant, so that we can combine both these. So now we have minus e raised to 2 times y over x, because v is y over x, and here we have 2, and by the properties of log, we can now write log of kx. So now we have e raised to 2y over x is equal to minus 2 times the log of kx. And here we have used the property, that is log of mn is equal to log of m plus log of n. So viewers, this is the general solution of this differential equation containing the constant that is k, right? So we have e raised to 2y over x is equal to minus 2 times the logarithm of k times x. So now let us find out the particular solution of this differential equation when we have the initial conditions as y of 1 is equal to 0, right? So when we have y of 1 is equal to 0, it implies that when x is 1, y is equal to 0. So let us substitute these values in this general solution to get the value of k. So we have e raised to 2 times, here we have y0, so we have here y over x is equal to 0. Then we have minus 2 and log of k times 1, because x is equal to 1. So here we have e raised to 0, this is minus 2, this is log of k. E raised to 0 is 1, so we have minus half is equal to a log of k, right? So k can be obtained by taking the exponential of this number, that is minus half. So k is equal to e raised to minus half, that is equal to 1 over e raised to half, that is 1 over square root of e. So now substituting this value of k in this equation, we have e raised to 2y over x is equal to minus 2 log of x over square root of e, right? So now let us simplify this expression by rearranging the terms. So we can now write e raised to 2y over x is equal to log of x over square root of e raised to minus 2, right? So now we have e raised to 2y over x, and here we can write e over x square, right? Because here we have x raised to minus 2, and here we have e raised to half times minus 2, because when we distribute this negative 2 to x and square root of e, then here this 2 and this 2 get cancelled, and x raised to minus 2 comes to the denominator. So we have 1 over x square, and here we have e raised to minus 1. So e raised to minus 1 goes to the numerator. So we have e raised to 1, right? So e raised to 2y over x is equal to the natural log of e over x square is the particular solution of this differential equation provided y of 1 is equal to 0.